Here on the ArcMin channel, the Real Analysis video series, lecture 28, series of functions. Okay, so let's define things. What is a series of functions? We looked at sequences of functions, now we're going to do series of functions, similar to how we looked at sequences of real numbers and then series of real numbers. So let that be a sequence of functions from a subset of Rn to the set Rm. Then for every x in A, we define the series f of x is equal to the sum n equal 1 to infinity of fn of x. And that is going to be the limit as k goes to infinity of this big Fk x, which we define as the limit as k goes to infinity of the sum this being the pointwise limit, provided the limit exists. There's nothing really to highlight here. I guess this series, that's right, series of functions. Okay, and some terminology, we say this series converges pointwise if these partial sums converge pointwise, and we say it converges uniformly if the FKs converge to F uniformly as well. All right, now let's look at an example of a series of functions. So take this for example, sum k equals 0 to infinity of xk over k factorial. This might look familiar, but if it doesn't, it will soon. And it's defined on R. Then for any x in R, the limit as k goes to infinity is x k plus 1 over k plus 1 infinity or factorial x k over k factorial, which is just equal to the limit as k goes to infinity. If you cancel everything out, the xk goes away and just leaves an x, and the k plus 1 factorial over k factorial just becomes a k plus 1. So that is x over k plus 1 is equal to 0, less than 1. So by the ratio test, this series converges pointwise. Now let's look at another thing. equals 0, x to the k, on the domain -1 to 1 as an open interval. Xk converges pointwise to 1 over 1 minus x. So we'll write that sum of xk is equal to 1 over 1 minus x pointwise. As another example, we take f defined from the closed interval from 0 to 1 to the real numbers as fk x 1 0 should be fk, it's fine that way, and x is in 0 to 1 over k, it's 1. If x we'll just write otherwise, it's 0 everywhere else. So if you look at fk of x, it's, what is it? Let's look at what happens at the endpoints. So if you take fk of 0, it will just be outside of this open interval, so it will be 0 everywhere, plus 0. And if you look at fk of 1, it will be also outside of this interval, because that will never have 1 inside. So that's also zeros. There's no 0 at the end since it's infinite. Let's move that over. So that is equal to 0. That is also 0, not a weird alpha. Now for the everything in the middle, if 0 is less than x is less than 1, then there's this natural number n such that 1 over n plus 1 is less than or equal to x is less than 1 over n. Note that f1 of x is equal to f2 of x is equal to fn of x is equal to 1. So that would mean if you sum them up, then you'd have n ones and then the rest 0. So that would give you n. So if you look at 0 is less than x less than 1 over n plus 1, this converges to 0. Okay. So we found the sum for everything in the domain. Now let's see. If fk is from this set of continuous functions from the subset A of Rn and has codomain Rm, and the series converges uniformly, then f of x is equal to the sum is continuous. And that is from what we showed before. If each fm, where's the partial sums of the functions up to m, they are in the set C from A to Rm, and since the Fm, that series converges to F uniformly. F itself must be continuous. Okay, now let's look at a convergence test. You might have seen these before for series on real numbers. You can also have convergence tests for series of functions. This one is the Weierstrass or the Weierstrass M test, which is saying suppose we have a sequence of FKs. It's a sequence of functions from a subset of Rn to Rm. Now suppose there's the sequence Mk, where each Mk is a real number, such that there's a natural number n with the infinity norm of Fk less than or equal to Mk for all k greater than or equal to n. Then if the series of Mk converges, then the series of Fk converges uniformly. And why is that the case? Well, look at Fk minus F, that infinity norm, if you sub everything in, the supremum over x and a. I'll just write x so it's less messy. That's the sum from I equals 1 to infinity by x minus the sum from I equals 1 to k. I'm just going to switch the order just so this next step is easier. Then if you look at the indices, this is just the same as a sum from I equals k plus 1, because you subtracted everything from 1 to k, from I equals 1 to k, to infinity of fi of x. And from the triangle inequality, the norm of a sum is less than or equal to the sum of the norms. So we move that in. And this is less than equals less than or equal to k plus 1 to infinity of the supremum, which we said was bounded by mk, but here the I. And this holds for k big enough. But since the sum of mi's goes to 0 as k goes to infinity, so that's why we get uniform convergence. So for example, infinity, n equals 1, we take 1 over x squared plus n squared, defined on the whole real number line. And that is just equal to what we have here, which is sup x in r, 1 over x squared plus n squared, which if you want the supremum, you'll set x to 0, so 1 over n squared. So otherwise it'd be smaller, since 1 over n squared converges by the m-test, which you might have seen in a calculus class. Then 1 over x squared plus n squared converges uniformly. And finally, if you take the sum infinity to n equals 0 of x to the n factorial on this interval from negative a to a for positive a, then that infinity norm and factorial will be a n over n factorial, and the sum of those a_n's over n factorial converge by the ratio test. So by the m-test, the Weierstrass m-test, this converges uniformly. And in particular, if f is from negative a to a goes to r, then fx equals xn over n factorial is continuous, since we had uniform convergence. Since a was arbitrary, if you take f from the reals to the reals as a goes to infinity, then this function is continuous as well. And that is it for this lecture.